Section 5.4, Head-on elastic collisions. In this section, we're going to look closely at perfectly elastic head-on collisions. Head-on collisions are impacts in which two objects approach each other from opposite directions. Because they are perfectly elastic, remember that momentum and kinetic energy are conserved after the collision. In fact, we can combine these two concepts, the concept of conservation of momentum and conservation of kinetic energy, to allow us to come up with simplifications in the equations that allow us to determine the final velocity of object number 1 and the final velocity of object number 2. You can take a look in your textbook to see how these equations were derived. In fact, it's kind of helpful to understand where they came from. You're not responsible to derive them yourself, but I do recommend that you take a look. We'll also look at a special case in which one of the objects is initially at rest. And we have two simplified equations, one for the final velocity of object number 1 and one for the final velocity of object number 2, in which object number 2, in this case, is initially at rest. Look carefully at these equations and compare them to the ones that you have in your notes. I had to make a change. There was a small correction, so just make sure they read as they do in this video. Let's try sample problem number 1. A head-on elastic collision with one object at rest in one dimension. Consider an elastic head-on collision between two balls of different masses, as shown. The mass of ball 1 is 1.2 kilograms, and its velocity is 7.2 meters per second west. The mass of ball 2 is 3.6 kilograms, and ball 2 is initially at rest. Determine the final velocity of each ball after the collision. So we're going to use these two equations, one for the final velocity of object number 1 and one for the final velocity of object number 2. Again, remembering to make sure they're written as they are in this video. And we can sub and solve these values to determine the final velocity of object number 1 and the final velocity of object number 2. Let's begin. For the final velocity of object number 1, it is equal to the mass 1, 1.2 kilograms, minus mass of number 2, 3.6 kilograms, divided by 1.2 kilograms, plus 3.6 kilograms, times the initial velocity, 7.2 meters per second. And it's important to include direction, west. If you punch this all into your calculator, you end up with a final velocity for object number 1 of negative 3.6 meters per second west, or we can write this as 3.6 meters per second east. Let's do the same for the final velocity of object number 2. It's equal to 2 times mass number 1, 1.2 kilograms, divided by 1.2 kilograms plus 3.6 kilograms. Multiplying this by the initial velocity of object number 1, 7.2 meters per second west. Punch this all into your calculator, and you should get 3.6 meters per second west. Therefore, the final velocity of object number 1 is 3.6 meters per second east, and object 2 is 3.6 meters per second west. Very good. Let's take a look at sample problem number 2. This is a head-on elastic collision with both objects moving in one direction. In bumper car ride, bumper car number 1 has a total mass of 350 kilograms. Since these are perfectly elastic head-on collisions, we can use the simplified equations for final velocity of object number 1 and the simplified equation for final velocity of object number 2. So let's go back to the question. In bumper car ride, bumper car number 1 has a total mass of 350 kilograms and is initially moving at 4 meters per second east. In a head-on completely elastic collision, bumper car 1 hits bumper car 2. The total mass of bumper car 2 is 250 and is moving at 2 meters per second west. Let's calculate the final velocity of each bumper car immediately after collision. Let's sub in these values. We have 350 kilograms minus 250 kilograms divided by 350 plus 250 kilograms multiplied by initial velocity and include direction. In this case, it's 4.0 meters per second east plus. It's a good idea to establish convention. And in this case, we're going to make east positive. We often just skip this step, and that's okay as well. But just make sure that you're acknowledging direction, especially when using the conservation of momentum, which requires direction. So continuing, 2 times 350 kilograms divided by 350 plus 250 multiplied by the initial velocity of object number 2. I'm going to write it as negative 2.0 meters per second east because it is positive 2.0 meters per second west. Punch this into your calculator. And just a reminder of what we did with the direction, changing it. You should get 1.0 meters per second west as your final answer. Now let's set off to determine the final velocity of object number 2. We can start subbing and solving. We have 250 minus 350 over 350 plus 250 times the initial velocity of object number 2, which is 2 meters per second west, or negative 2.0 meters per second east, keeping the direction the same. Trace it in red so that you remember. Plus 2 times 350 divided by 350 plus 250 times the initial velocity of object number 1, which is 4.0 meters per second east. Punch this into your calculator, and you should get 5.0 meters per second east. Therefore, the final velocity of bumper car 1 is 1 meter per second west, and the final velocity of bumper car 2 is 5 meters per second east. Okay, let's look at some special cases. The first special case is in which the objects have the same mass. Now, There are a lot of practical applications of this. For example, if you ever play pool, you know that all the billiard balls have the same mass. So you can observe some of the concepts and even predict some of the behaviors. We'll assume that M1 is equal to M2, and we'll just call this mass M. So simplifying the equations from above, we'll write M minus M over M plus M times VI1 plus 2M over M plus M times V1, 2, or V initial 2. Now M minus M is 0. If the numerator is 0, then this whole term is 0. For the second one, we can simplify it. We have 2M divided by 2M times V1, 2. So the final velocity of object number 1 is equal to the initial velocity of object number 2. Once they contact each other, it's as if they exchange velocities. So these two objects exchange velocities almost as if the velocities pass through each other. Let's take a look at a second special case, the case in which one of the two objects is much heavier stationary object. So much heavier, in fact, that the mass of object number 1 is almost insignificant. I want you to picture this in your head. Send a small, very small object colliding towards a very large object, where the mass of number 1 is way smaller than mass number 2. Imagine what you think will happen. Well, let's use mathematics to see what happens. Now, I apologize in advance if I haven't given you enough room. Just want to block off this area so that we can write our observations and do some rough calculations. So if mass 2 is significantly greater than mass number 1, we can assume that mass number 1 is equal to approximately 0. So we have 0 minus m2 divided by 0 plus m2 times the initial velocity of object number 1. Now let's simplify this. This ends up being negative m2 over m2 times the initial velocity of object number 1. m2 divided by m2 is just 1. So we end up with negative v initial 1. So what this tells us is when a small object collides with a larger object, its velocity has the same magnitude but is in the opposite direction. So essentially what happens, the velocity of the smaller mass or the lighter object is reversed, as if it is deflected off that very large object, and the large object remains at rest. Let's confirm that the large object remains at rest by taking a look at the equation. Remember, this is a simplification for the final velocity of a second object if it was initially at rest. So it's 2m1 divided by m1 plus m2 times the initial velocity of object number 1. Since m1 is approximately 0, we can say that the final velocity remains 0. The object remains at rest. Velocity of the more massive object is 0. Okay, let's take a look at this common experiment done in the conservation of mechanical energy. We have two gliders, a blue glider and a yellow glider. The blue glider is traveling to the right with a velocity of v1, and the yellow glider is traveling to the left with a velocity of v2. Now on the yellow glider, you will notice that there's a spring bumper. When these two collide, it will compress the spring bumper. So during the energy transformation, there will be a component of the energy transformation that is converted into elastic potential energy. When two gliders collide, the duration of the collision is greater than it would be without the spring bumper on one of the gliders. And if the compression of the spring bumper is x, then the law of conservation of energy states, and let me go through this, highlighting each of the terms so you know where they come from and what they mean. The initial kinetic energy of the blue glider plus the initial kinetic energy of the yellow glider is equal to the final kinetic energy of the blue glider plus the final kinetic energy of the yellow glider plus the elastic potential energy of the spring bumper. If you take a look at this graph, the blue line denotes the total kinetic energy possessed by the bumpers, or by the gliders rather. And notice that it's only during the collision that there's an exchange between kinetic energy and elastic potential energy on the bumper. The green line represents the elastic potential energy, and we notice that when it is a maximum, the kinetic energy is a minimum. So we can state that the total mechanical energy remains constant Okay, let's do an example of one such system. We have two dynamics carts with a spring in between them. Dynamics cart 1 has a mass of 1.8 kilograms and is moving with a velocity of 4 meters per second right along a frictionless track. Dynamics cart 2 has a mass of 2.2 kilograms and is moving at 6 meters per second left. The carts collide in a head-on collision cushioned by a spring with a spring constant, K equals 8 times 10 to the power of 4 Newton meters. In part A, they want us to determine the compression of the spring in centimeters during the collision when cart 2 is moving 4 meters per second left. In order to solve this, we're going to be combining the law of conservation of momentum for these two moving carts and substitute the values found into the conservation of mechanical energy. So for part 1, let's begin with the conservation of momentum. M1 V1 initial plus M2 V2 initial is equal to M1 V1 final plus M2 V2 final. We're going to take this opportunity and solve for V1 final. So rearranging, we have V1 final is equal to M1 V1 initial plus M2 V2 initial minus M2 V2 final divided by M1. And we can start subbing in our values to find the initial final velocity. It's 1.8 kilograms times a velocity of 4 meters per second right. And again, because we're dealing with momentum, we need direction, plus 2.2 kilograms times an initial velocity of negative 6 meters per second right. And just so that we remember what we're doing here, it was 6 meters per second to the left, but we're keeping all the directions the same. So let's make right positive. Minus, at the time of the impact in which we're concerned about the compression of the spring, the velocity of object number 2 is 4 meters per second to the left, or negative 4 meters per second right. Again, I just want to highlight that we have changed the direction. And now we can sub and solve. If we do, we end up with 1.56 meters per second to the right. I'm keeping an extra digit here just so we can begin the second part. In the second part, we're going to use the conservation of mechanical energy to determine the compression of the spring. We can incorporate this value that we just found, 1.5 meters per second, into the conservation of mechanical energy. So let's use the conservation of mechanical energy to determine the compression of the spring. So the conservation of mechanical energy says the kinetic energy of the first object plus the initial kinetic energy of the second object is equal to the final kinetic energy of the first object. Clear that up. Final kinetic energy of the first object plus the final kinetic energy of the second object plus the elastic potential energy of the spring during this collision. Now there are 1/2 in front of every term in each side of the equation, on each side of the equation. So if we multiply both sides by 12, or by 2 rather, we can get rid of these 1/2 and solve for x. Let me get rid of that 1/2 as well. We can rewrite this without the 1/2. It allows us to see these terms more clearly. So m1 v1 initial squared plus m2 v2 initial squared equals m1 v1 final squared plus m2 v2 final squared plus kx squared. Solving for x, x is equal to the square root. Move this over to the left if you haven't started writing, because we'll need more room to solve this. Of square root of m1 v1 initial squared plus m2 v2 initial squared minus m1 v1 final squared minus m2 v2 final squared. All divided by k. Let's sub and solve. This will take up even more space. 1.8 kilograms times 4 meters per second. Now, because we're dealing with kinetic energies, we don't have to include direction, squared plus 2.2 kilograms, initial velocity of 6 meters per second, square it, minus 1.8 kilograms, a velocity of, we just found, it was 1.56 meters per second, minus, in the question, 2.2 kilograms times a final velocity of 4 meters per second squared. They tell us to find x when object 2 is traveling at 4 meters per second. Divide this by the spring constant, 8 times 10 to the power of 4 newtons per meter. Punch this lengthy equation into your calculator carefully, and you should end up with 2.9 times 10 to the power of negative 2 meters, which is 2.9 centimeters. So the compression of the spring during the collision when cart 2's speed is reduced to 4 meters per second to the left is 2.9 centimeters. Let's take a look at the final problem. In part B, they want us to calculate the maximum compression of the spring in centimeters. Now it's important to note at the time of maximum compression, the velocities of cart number 1 and cart number 2, or glider number 1 and glider number 2, will equilibrate and will be the same. So the final velocity during maximum compression will be the same, and we'll call it VF. We're going to solve this in 2 parts. The first part is to determine the final velocity, and then we're going to use this final velocity to find the compression x. So we have m1 v1 initial plus m2 v2 initial is equal to the final velocity times m1 plus m2. Solving for final velocity, or rearranging for final velocity, we end up with m1 v1 initial plus m2 v2 initial divided by m1 plus m2. Now we can sub in our values. So that's 1.8 kilograms times an initial velocity of plus 4 meters per second plus 2.2 kilograms times negative 6 meters per second. Remember, 4 is east and 6 is west, divided by 1.8 kilograms plus 2.2 kilograms. Punch this all into our calculator, and we end up with negative 1.5 meters per second. That's the final velocity of these 2 objects during maximum compression. Now, let's use the conservation of mechanical energy to determine the max compression of the spring. So let's write out the conservation of mechanical energy. It's 1/2 m1 v1 squared plus 1/2 m2 v2 initial squared, and it's equal to 1/2 m1 plus m2 v final squared. So remember, they have the same final velocity, plus 1/2 kx squared. We can get rid of the 1/2 just as we've done in the past, multiplying both sides of the equation by 2, reducing this. So if we solve for x, I'm going to do this all in one step, so bear with me. m1 v1 initial squared plus m2 v2 initial squared minus 1/2 m1 plus m2 times the final velocity squared, all divided by the spring constant k. Sub and solve. 1.8 kilograms times 4 meters per second squared plus 2.2 kilograms times 6 meters per second squared minus 1.8 plus 2.2 kilograms times a final velocity of 1.5, no need to put direction because these are scalar quantities, squared divided by the spring constant 8.0 times 10 to the power of 4 newtons per meter. Now let's punch this into our calculator, and you should end up with 3.5 times 10 to the power of -2 meters, or 3.5 centimeters. Therefore, the maximum compression of the spring is 3.5 centimeters. And this happens when the two gliders are colliding and their velocities equilibrate. So take a look at practice problems on page 243 and 247, as well as review questions on page 248.